Hi students, in this final video for online lecture 17 and chapter 9, we are now going to talk about the redox reaction. So the redox reaction stands for the reduction oxidation reaction. As we previewed a little bit back in our first online lecture for this chapter, this is all about electrons moving instead of atoms. So let's take a brief view at this reaction. So as you will see here, I am going to have our zinc inside of a copper solution. So as you will see here, our copper is what is causing this blue solution that you see in our left figure. As our zinc picks up and goes and transfers electrons to that copper. So in this case, remember that if you are losing electrons, this is going to be the oxidation. So our zinc is going and oxidizing, losing the electrons, and our copper is going and gaining them, forming our copper solid. So that is one type of redox reaction. Let us go ahead and look at our right diagram. You will see once again that you are going to have a new solution. This time, you are going to have a copper solid, and in our solution, you are going to have our silver cation. Meow. In this case, our copper is going to go and convert from a solid to an ionic species, giving off the 2 electrons that is necessary to go and reduce our silver. So if I have 2 electrons and silver only needs 1 electron to go from silver plus to silver solid, this means that 1 copper atom can go and reduce 2 silver atoms. In our right figure, you are going to see the silver that is created here as this spiky white material. During these reactions, we have shown you how atoms are going to lose electrons, that being the oxidation. Then we are going to have atoms that gain the electrons. That is going to be the reduction. So let's look at this reaction here. We have zinc solid and copper sulfate going to zinc sulfate and copper solid. Let us look specifically at the zinc. If we have our zinc solid, we are going to have it in its elemental form, and its oxidation number, which we will see here in a moment, is going to be 0. In zinc sulfate, it is actually zinc 2 plus. So in order that to happen, we are going to have lost 2 electrons. This, by definition, is going to be our oxidation. So let's talk about the reduction side. Our copper is copper 2 plus in our copper sulfate, but over on the right side, it's in its elemental state, so it would be copper solid. This means that the 2 electrons that we are losing from our zinc are going and being donated to our copper. So while we have our oxidation, the bottom reaction is going to be our reduction. So let's talk about some of the terminology. So because zinc is losing electrons, the electrons are on the product side, this by definition means that it is going to be oxidized. But the problem with that is that we use an older naming system for this reaction. We are going to call zinc the reducing agent. Agent meaning the species that is going to cause something else to happen. So if zinc is going to be the reducing agent, this means that we are going to reduce another atom. So in order to reduce another atom type, we therefore must be oxidized. So be careful as you're looking through your reactions, because we might say, look for the oxidized atom, and then the next question we might say, what is the reducing agent? And we are literally asking for the same thing. So now let's go ahead and look at our reduction. You can see that our copper 2 plus is gaining electrons. Those electrons are on the reactant side. This is a hallmark of our reduction. Well, if our Cu2 plus is being reduced, very much like we had for our other species, an oxidizing agent is the one being reduced. This is because our oxidizing agent is oxidizing another atom. So as we go through our terminology, remember that you can always think of a very nice process. Is it gaining or losing electrons? What does that mean for the name? And then a lot of students will say, oh, it's just opposite, but it's not. Remember that if you're the reducing agent, you must reduce another atom. That means you therefore must be oxidized, and vice versa for our oxidizing agent. Let's take a look at this in an example. This is an example from the fall of 2015. So let's identify the reducing agent in the following redox reaction. So now with it being a reducing agent, we know that we must look at one of our reactants. So let's go and work through the terminology. Remember that for a reducing agent, this is going to be the species that is oxidized. If it is going to be oxidized, does that mean that it is gaining or losing electrons? This means that it is going to be losing electrons. So now we need to take a very quick look at our balanced chemical equation to see which species is losing electrons. So what can it be? Well, if I go ahead and look at my Cl2, you will notice that it is gaining electrons in order to form our Cl-. Gaining electrons means that it is going and doing the reduction. That would be the oxidizing agent. So our chlorine and chloride are going to go off the table. Now let's go ahead and look at our H plus and our H2O. Our H2O is going to have two oxidation numbers. Our H plus is going to be 1 plus. Those rules will be described here momentarily. And oxygen will be 2 minus. And the interesting part is that our hydrogen keeps the same oxidation number. If that occurs, it does not participate actively in the transfer of electrons. So D and E are going to be incorrect answers. So by a process of elimination, you would get A as the answer. Let's talk about how this is the case. For our sulfite, our oxygen has a -2 oxidation number. In order to balance our oxidation numbers correctly, our sulfur in here must be +4. We will show you how to do that here in the coming slides. When we go to the other side and look at sulfur in my sulfate, our oxygen is still going to be -2, but now because we've added another oxygen, our sulfur is now going to be +6. So in the case of sulfur, to go from +4 to +6, remember that becoming more positive means that you are going and being oxidized. This, by definition, is going to be the reducing agent. So let's take a look at how we calculate the oxidation numbers. There's a few rules that we are going to go through. The first one says the charge the atom would have in a molecule or ionic compound if the electrons were completely transferred. So this is going to be different than many of the numbers that we have calculated previously, such as formal charge, and just as our charge on a molecule normally. This is going and saying that we are going to completely transfer those charges. So the first rule that we have is that free elements in their uncombined state have an oxidation number of 0. This is a rule that you have seen me use in multiple videos now. So if it's in its elemental state, it is going to have an oxidation number of 0. This is going to benefit us in many redox reactions. Our second rule says for the monoatomic ions, the oxidation number is equal to the charge on the ion. This means that if we are able to describe our ion using one of our elemental charges that we have used previously during our nomenclature chapter, we are able to easily assign that with an oxidation number. So lithium, which is in column 1, if it goes to lithium plus, we know it will be +1. If we have iron 3, this oxidation number would be 3+, and as you see here with oxide, it would become 2-. The oxidation number for oxygen is usually, notice that this is bold, is -2. In hydrogen peroxide and the peroxide anion, which is O2 2-, it actually gets the value of -1. So when it comes to oxygen, we will historically have it be -2. This is going to help you out when you are trying to determine the oxidation numbers of many of your polyatomics. Let us go to rule 4 that states the oxidation number of hydrogen is +1, except when it is bonded to a metal in a binary compound. If it is a binary metal compound, then the oxidation number is -1. So what does that mean in this case? If I have sodium hydride, my sodium would be +1 and my hydride would be -1. This would be different than, say, HCl, in which Cl would be 1- and our hydrogen is 1+. So when dealing with the oxidation number of hydrogen, if the hydrogen is bound to a metal, it is -1. If it is bound to a nonmetal that is more electronegative, then it will become +1. For rule 5, group 1A metals are always +1. The 2A metals are +2, and fluorine is the only halogen in which we are sure we can assign a -1. The other halogens are going to show a great variety of the oxidation numbers that you will see. In the 6th rule, the sum of the oxidation numbers of all of the atoms in the molecule or ion must equal the charge on that molecule or ion. And finally, for rule 7, the oxidation numbers do not have to be integers. The best case of this is what we call superoxide, which is O2 1-. This means that we must separate the -1 charge over 2 atoms, and that is how you'll get -1/2. This is one of the rare examples in which you will see this. So let's look at some of the common oxidation numbers using the periodic table. As you can see in our 1A group, the only one that shows any variety is hydrogen, and that was described in a previous rule. But you can see for lithium, sodium, potassium, rubidium, and cesium, they are always +1. In the case of our alkaline earth metals, notice that they are all +2. Once we get into the transition metals, you can now see the variety of the oxidation numbers that you are going to get. Chromium is going to have the possibility of 5 different numbers, the same with manganese. So now when we get one of these species, we are going to have to use context clues and be sure of other species to make sure that we assign those metals properly. Then you can see as we are going to our halogens, here is fluorine at -1. This is the only one that we are sure of. Then go ahead and look at chlorine. There is a multitude of oxidation numbers. It actually can adopt 7 different numbers. So when chlorine is the most electronegative, it really likes to be -1. But if there's another atom, historically oxygen involved, it is going to go and turn it into a positive oxidation state. So what we need to do is work really hard on a few examples trying to figure out what species we have and what oxidation numbers we can calculate. So let's go ahead and try this example. Assign oxidation numbers to all of the elements in the following compounds and ions. So let's look at A. Is there a species that we are sure of? We should be 100% sure of our cesium. This is a 1A metal. Because of that, our cesium is going to have individually a +1 charge because of its location in the alkali metal group. If there are two cesiums, what does that mean for our charge on our sulfur? Well, because this is sulfide, we know that this is going to be -2. So we can successfully state that our cesium is +1, while our sulfur is -2. Let us go ahead and go to example B. In here, if you have three different elements, you are going to be fairly confident of two, and you will use the information from those two in order to determine the third. So which one are we pretty confident in? Well, that one is going to be potassium because it is in column 1. So our potassium is also going to be +1. The next one that we are probably the most sure of is our oxygen, because it being the most electronegative atom in this compound, this goes by the oxygen is usually -2. So now we can use this information in order to determine the oxidation number for my nitrogen. So if I have my potassium at +1 and each one of my oxygens is -2, this means that the remaining charge in this compound is going to be the oxidation number for nitrogen. So if you'll see that I have a total of -6, 3 times -2, +1, you will come to find out that the nitrogen is going to be equal to +5. Because nitrogen can adopt so many different oxidation numbers, it is best to use the context clues in order to determine that value. Let us go ahead and go to example C. In this case, what atom in this do I know the most about? Well, because oxygen is going to be the most electronegative, we know that it is going to be -2. There are 7 of them. That means that there is going to be a total negative charge of -14. So now what I have to do is find the value for my chromium at 2x, but it still needs to leave a -2 charge. So if I take my -14, move it to the other side and make it +14, you will come to find out that my 2x equals 12. So then if I divide both sides by 2, you will come to find out that my chromium, each one of these is going to be 6. So when assigning this, we can say that my chromium is equal to +6, while my oxygen is going to have its normal ionic state of -2. Determining oxidation numbers is not only going to help us in this chapter, but when you get to the electrochemistry chapter in your Chem 120, you are going to revisit this topic and it will help you balance your redox reactions. So let's try one final example, and this comes from the fall of the 2015 exam. What is the oxidation number of the chlorine in ClO1-? So this is the hypochlorite ion. So now what we have to decide is there an atom in this that we are most confident in? This confidence comes from our oxygen. Remember that our oxygen is going to be -2 in most cases. So if that is -2, I need to determine the value for my chlorine that will result in a -1 charge being left over. In this case, you are going to see that my value for chlorine is going to be equal to +1. So while you are used to seeing chlorine as -1, in the hypochlorite anion, this is one of the examples in which you will see it as +1. So if I were to look at my answers at the left, you will see that a correct answer is going to be answer B. In this video, you saw the importance of the redox reaction in which we are transferring electrons. While it may be very difficult to see that electron transfer, we have now given you the rules of the oxidation numbers to hopefully make it easier and help you with your transition as you go and see your electrochemistry chapter much later in the next course. Have a great day.